Welcome to this explainer. Okay, let's get right into it. Have you ever stopped to think about how your computer actually remembers things? From your deepest, most buried file archives to that browser tab you literally just opened, it all relies on some incredibly clever hardware. Today, we're going to demystify the fundamental building blocks of all computer memory. We are looking at sequential circuits. Here's our roadmap for today. We'll meet the sequential circuit, build a basic SR latch, upgrade it to a D latch, dive into flip-flops and clock pulses, lock it down with the master-slave configuration, and wrap up with the characteristic equations. These concepts build directly on one another, so let's jump right in. Section 1. Meet the sequential circuit, the memory blueprint. To really appreciate memory, we first have to understand what a system looks like without it. On one side, we have combinational circuits. These have zero memory. Their output depends entirely on whatever's being fed into them right at this very second. But sequential circuits, they include specific storage elements. Their output relies on the current input, sure, but also on past states. So the big takeaway here is that sequential logic gives our hardware the ability to actually look back at its own history. Take a look at this block diagram. See that line looping from the memory elements box right back around into the combinational circuit box? That feedback loop is literally the magic ingredient. It grabs the previous state, cycles it back as a fresh input, and just like that, boom, we've created digital memory. Section 2. The basic SR latch, the foundation. So how do we actually engineer that basic feedback loop? Well, we use logic gates. Here we're comparing two different architectures for the SR latch. On the left, it's built using two cross-coupled NOR gates, and on the right, two cross-coupled NAND gates. By the way, SR stands for set and reset. By feeding the output of one gate directly into the input of the other, you can see that crossing pattern there, we create a circuit that can lock or latch onto a state of 1 or 0. Section 3. The D-latch upgrade, fixing the glitch. It's an elegant design for sure, but there's a hidden, fatal flaw. To understand it, we have to ask a kind of dangerous engineering question. What happens if set and reset are triggered at the exact same time? Basically, what happens to our hardware if we scream turn on and turn off simultaneously? Well, as you can see in the function table on the right, the answer isn't pretty. We've added a control, input C, to our SR latch so we can govern when it changes. But look at that bottom row outlined in red. When both S and R inputs equal 1, we hit what's known as the indeterminate state. The circuit gets completely confused. This is a massive hardware vulnerability, and frankly, it's something we absolutely cannot allow in reliable computer systems. Enter the D latch. This clever logic diagram is the brilliant engineering workaround that eliminates our indeterminate glitch entirely. Notice how the data input, labeled D, is routed. It feeds directly into the top gate, but it's forced to pass through an inverter, that little triangle symbol, before hitting the bottom gate. This mathematically ensures that the set and reset inputs can never, ever be equal to 1 at the exact same time. Problem solved. Now, when you're looking at massive schematic diagrams for complex electronics, you're obviously not going to see every individual logic gate drawn out. Instead, you'll see these simplified rectangular blocks. On the left, we've got our standard SR latches, and on the right, our upgraded D latch, neatly packaged up with inputs on the left and outputs on the right. Section 4. Flip-flops and clock pulses, perfecting timing. Okay, so we fixed the indeterminate state issue. Awesome, but we still have another hurdle: timing. Before we look at the wiring, let's quickly define a crucial piece of jargon. A trigger is a momentary change in a control input that initiates a state switch in a latch or flip-flop. Think of it like a conductor's baton. It's the exact precise signal that tells the digital memory to update its state. So how does that trigger actually operate in practice? This graph illustrates something called positive level response. See those thick black bars at the top of the square waves? In a standard latch, as long as the clock pulse stays up at that logic 1 level, the door is open. If the D input changes while that pulse is high, the output changes too. The problem is, leaving the door open that long can sometimes let unwanted electronic noise slip right on through. To fix that noise problem, we rely on a massive upgrade known as edge triggering. Check out the little arrows on those waveforms. Instead of leaving the door wide open for the entire duration of the pulse, a flip-flop strictly confines state changes to the very instant the clock signal transitions, either on the positive edge going up or the negative edge going down. It's instantaneous, it's precise, and it drastically cuts down on errors. Section 5. The master-slave configuration, ultimate reliability. To make this edge triggering technique even more robust, engineers developed a totally fascinating trick. Notice how we combine two separate components to work as one perfectly timed unit here. We've got a D latch on the left, which acts as the master, and a D latch on the right, which acts as the slave. I really want you to direct your attention to the clock input down there at the bottom left. The clock signal feeds straight into the master, but it gets forced through an inverter before it ever reaches the slave. That single inverter creates this beautifully sequenced two-step dance. In step 1, the master latch samples the data input while the clock pulse is high, but because of that inverter, the slave is completely locked out. Then in step 2, the exact moment the clock drops to its negative edge, the master locks in its data and the slave opens up to pass that data to the final output. This kind of isolation guarantees the output won't accidentally flip while the input is still trying to settle. Now, the master-slave setup is great, but you know engineers, we love efficiency. So here's an alternative, highly efficient construction for an edge-triggered D flip-flop. Instead of using two whole D latches, this design uses three tightly interlocked SR latches. The two latches on the left interact directly with the data and clock inputs to prep the signal, while the third latch on the right provides the final stable output. Section 6. The characteristic equations, the mathematical core. We've spent a lot of time looking at physical logic gates, so let's translate everything into its mathematical core. But right before we dive into the pure math, let me show you one final hardware configuration, the T flip-flop, where the T stands for toggle. As you can see, this is simply our trusty D flip-flop, but we've bolted an exclusive OR gate right to the front of it. This creates a memory element that simply flips its state to the absolute opposite of whatever it was every single time it receives a trigger pulse. All right, here's the crucial takeaway. All of this complex physical hardware we've been talking about can be perfectly modeled using these characteristic equations. The term Q of t plus 1 represents the predictive next state of our digital memory. For the D flip-flop, the next state is wonderfully simple. It's just whatever D happens to be. The JK flip-flop is a bit more complex, relying on the current state and inverted inputs. And our T flip-flop effectively uses that XOR function we just saw. These equations are literally the mathematical heartbeat of all sequential logic. Wow, we've covered a ton of ground today, haven't we? From the pure magic of the very first memory feedback loop to those perfectly timed edge-triggered mathematical equations. Now that you understand the fundamental secrets of latches and flip-flops, how will you use these tiny building blocks to engineer the complex digital memory systems of tomorrow? Thanks for joining me on this explainer, and keep learning.